Well, now we're going to go ahead and talk about two extremely important theorems that are going to help us determine when functions are actually continuous. The nice part is that this will kind of really tie into a lot of functions that we already know and love from pre-calculus and algebra classes. So let's take a look here at the first theorem. The first theorem says, if f and g are continuous functions at a specific point, so maybe they're continuous, let's say x equals 1, and if c is a constant, then the following functions would also be continuous. So specifically, continuous at a. So if the first two functions are continuous at a point, these other functions are continuous at the same points. So notice here that this says if I have two functions, I could add them together to get a continuous function. I could subtract them to get a continuous function. I could multiply one of them by a constant. I could just multiply the two function formulas together. Or I could divide the two functions, of course provided that the denominator doesn't equal 0 at the given point, because then that would force me to divide by 0. Now, again, theorems in mathematics are really important large statements that introduce a big new idea. So theorems also take proof. You have to be able to justify the statements here. Now, we're not going to go ahead and justify each one of them, as that would take a decent amount of time. However, we will go through here briefly an explanation of how I would know property number 1 here. So let's take a look at what we have and think about what it is that we're trying to show. What we're thinking about is, if I already had two functions, f and g, that were continuous at a point A, how in the world could I definitely know for sure that the addition of those two functions would end up being continuous? Well, let's take a look here at what we have. So, I could say, we know that if f of x and g of x are continuous at x equals a, this of course means that the limit as x approaches a of f of x has to equal f of a. That's the definition of being continuous at a for the function f. But we would get the same sort of thing happening then for the function of g. Right? We know that this would have to be true. However, we still have to show that the function f plus g, we could imagine writing it as f plus g of x, that we have to show that that function is actually going to be continuous. So that would mean that we need to show that the limit of this function at a is actually equal to the y value at a. So let's go ahead and do that. So I'll start here by saying then we see that if I wanted to calculate the limit of f plus g of x as x approaches a, remember that's what I'd have to calculate here to start figuring out if this is continuous. Notice though I could kind of just use a limit law here, right? Because what I'm really working with right now is this is the same thing as saying that I have the function, or that I'm taking the limit of the function f of x plus g of x, right? That's what this is. It's just the two functions added together. But since both of these functions have a limit, I can go ahead and use the limit law and state that this is really just the limit of the first function plus the limit of the second function, right? That would have to be true. And I already know, based on what I've seen up here, that since the function f is continuous, I already know what its limit is the same as. Its limit is the same as f of a, and so I could just replace that limit there with f of a. Similarly, I could replace this thing down here with g of a. And notice, doesn't that now look like the function f plus g just with a plugged in for all the x's? That is, isn't that really just f plus g with a plugged in? And if you look at what I've linked together here, we've then said that the limit of this function is equal to its y value. And so we've actually completed the justification. This function here would be continuous because its limit does equal its y value at the point of a. So this is a really, really interesting result. Okay? In a very similar way, you could write out proofs to many of these other numbered parts here of this particular theorem. Now, we won't go ahead and actually do that ourselves, but as I state down here, they are very similar. So if you're interested in trying those, give them a shot and see if you might be able to justify those to yourself as well. Now, we have one final theorem that we're going to talk about in this video, and it's this one. The following types of functions can actually be shown to be continuous at every number in their domain. Every number in their domain. That is, every time that you can plug an x in and get a y, these functions are continuous at those points. And let's take a look at the types of functions that we have here. We'll see this is actually really good news. So we have polynomial functions. Okay, so polynomials are great functions. They're simple. Remember, those are, nice things. Like an example would be like y equals x squared plus x plus 1. Polynomial functions, continuous. Rational functions like y equals x over x to the third minus 2, right? Root functions like y equals square root of x. Trigonometric functions like y equals the sine of x, continuous everywhere it's defined. Inverse trig functions, y equals, say, the arctangent of x, or tangent inverse. Exponential functions, like y equals e to the x. Logarithmic functions, like y equals natural log of x, right? These sorts of examples, these functions are continuous everywhere they have y values. That doesn't mean that these functions are continuous on every number ever, because as we know, some of these functions are not defined on every number ever. But everywhere they are defined, they are connected. Okay? So this is really awesome, because if you really think back to what you know about algebra and pre-calc, are there any other types of functions that you know of? Anything that wouldn't kind of fit into one of these categories? Not really. Because even if you're thinking things like, well, what about like cube roots or third roots or stuff like that, that's underneath root functions. Well, Kyle, what about something like x to the 4/3 power? Well, that is actually a root function. It just has, you just have to rewrite the exponent in terms of a root. So these are really the only functions that we know of, and this theorem is telling us that these functions are all continuous everywhere they're defined. So in the videos to come, we'll see how we're going to use these two extremely important theorems to help kind of expand what we know about continuity and how we can start to determine where really messy and complicated functions are and are not continuous very, very quickly.